Hello, what we're going to be working on today is the method of false position, which is a strategy that both the ancient Egyptians and the ancient Babylonians used. The Babylonians had a slightly different way of doing it, and they were able to actually do more advanced math with their method of false position, but the Egyptians were still able to accomplish a lot. And this came from the Rind Papyrus, which was written about 1650, I think, BC. And it dates back even earlier than that because the Rind Papyrus was just a copy of some sort of other resource that came before that. So we don't really know exactly how old this method was for the ancient Egyptians. So they use these to solve linear algebraic equations. So it's linear because they're both x. Neither of them have a squared or square root or anything like that. And nowadays we would solve these by just combining like terms and then dividing. And I'll show you that in a little bit, but for right now we'll look at how they did it using the false position. So the method of false position was sort of like guess and check, except it was more of just guess and then figure out the answer from the guess. So there was no checking and re-guessing or anything like that. So before I get into the actual problem, I just want to note that the ancient Egyptians never had equations. They never had x's, they didn't have pluses or equals or anything like that. All they really had was numbers. And so if the ancient Egyptians had a problem like this, like what you would see in the Rind Papyrus, it would actually be written as a sentence, and it would say, what is the value of heap if heap plus 1/8 of heap is 4? And so this unknown right here, they called heap. I don't know why they called it heap, but heap, H-E-A-P. Or they could also have called it aha. I don't know the significance of either of those two words, really, but that's what they called it. I don't know why. So this would be written as a sentence, and that would be a heap plus 1/8 of a heap is 4, and then they would solve it. So this was the algorithm that they used to solve it. They would pick a false value, okay? And the number that they picked they knew would be wrong, but it was just to kind of get them started. And the Egyptians understood these types of unit fractions with the 1 in the numerator, and so they knew that the best false value to pick for this would be an 8. So I'll show you in a second why the 8 works, but that's what they probably would have picked if they knew what they were doing. So I'm going to take that 8 and I'm going to plug it in for each of the heaps. So we have 8 plus 1/8 of 8. Okay, and so now you might see why I picked 8. It should be pretty obvious because these are reciprocals. 1/8 times 8 is 1. So we would actually have 8 plus 1, which is 9. So we picked a number, 8, we plugged it into this equation, and we got 9. We meant to get 4. So obviously this is not the right answer, but we can use that to figure out what the right answer is. And so the question we have to ask ourselves is 9 times what number equals 4? We're basically trying to figure out how far away from the right answer we are. So this would be 9 times 4/9, and that equals 4. Because the 9 and the 9 would cancel out, and then you would just have a 4 left. So basically, if you take our wrong answer and you multiply by 4/9, you get the right answer. Okay, so I'm going to call this the proportion value. I don't really know what the technical name is. Okay, so what they would do, we're basically done at this point, is they would take their proportion value and they would use it to scale the guess that they started out with. So they would take their guess, which was 8, and multiply it by that value over here that I got here, the proportion value, and multiply, and they would get 32/9, which is the right answer. And if you don't like improper fractions like that, you could also write it as 3 5/9. Personally, I prefer the improper fractions. I think mixed fraction is more of something you would see like in elementary school. Definitely not decimals, though. Nobody wants decimals. So either this fraction or this fraction, and that's your answer. Okay, and we can plug it back in up here and check it. So I'm going to plug in 32/9 plus 1/8 times 32/9 equals 4. Okay, the 1/8 and the 32 cancel each other out. So we have 32/9 plus 4/9, which gives us 36/9, which is 4. And so we see that when we plug in 32 over 9, we do in fact get the right answer. So this value of x really is 32 over 9. Okay. One more thing to note here before I move on to show the modern day version is that the Egyptians only used unit fractions, meaning that they had the 1 in the numerator. The exception is the fraction, the specific fraction 2/3. So this fraction 5/9 or this one 32 over 9 was out. They would not use it because it doesn't have a 1 in the numerator and it's not 2/3. So they would probably have written this as 3 plus 1/2 plus 1/18. So 1/2 plus 1/18 add together to give you the 5/9, and then you have the 3. So they would have actually written it out like this. And we're not really sure why they did that. We don't really know how they decided which unit fractions because there's more than one way to write 5/9. But this is probably 1/2 and 1/18 is probably how they would have written that fraction. Okay, so just to really quickly show you the modern day version of this. Okay, we want to combine the two x's because they're like terms, but before I can do that I need a common denominator. In this case my common denominator would be 8. So it's going to be 8 over 8x plus 1 over 8x equals 4. So I just multiplied this x by 8 over 8 so that I could have common denominators. And now I can put them together. So I'm just adding 8/8 plus 1/8 is 9/8. Okay, and then to get the 9/8 to cancel out, I can multiply both sides by 8 over 9. And you should kind of see we had 9 times 4 over 9, and here we have 4 times 8 over 9. They're kind of similar. So this ends up giving us 32 over 9, which works out to the same answer. So the fraction comes out just slightly different, but it ends up working out to give us the same thing. Oh, I'm sorry, I should have been looking here. I was pointing in the wrong place. 8 times 4/9, and here we have 4 times 8/9. So you see how they're almost the same. You just switch the numerators. So that's how we do it nowadays. This is how the Egyptians would do it. You can decide which way you like better. Either way works. And that's it for the video.